You're listening to The Star Spot, episode 67 for Sunday, December 14th, 2014.
I'm Justin Trottier, and I'll be your host at The Star Spot. The Star Spot is a space-themed podcast that focuses on all aspects of astronomy and space exploration. Episodes feature interviews with guests of wide-ranging backgrounds: scientists, engineers, educators, artists, politicians, and business people. Topics are similarly broad, from the latest space mission to how the universe began, from why humans explore to how we can make exploration economical. We'll also include a segment called Current in Space, bringing you reports on news and developments that may interest the space enthusiast. You can now find the show on Facebook at facebook.com/thestarspot or follow us on Twitter at thestarspot. The 1929 discovery of the expanding universe by Edwin Hubble forever changed our picture of the cosmos and our understanding of our place in the universe. In 1998, we learned that wasn't the only surprise. That's when two teams of astronomers announced that the expansion of our universe isn't slowing down as everyone assumed, it's speeding up. Today, I'm joined at the Star Spot by Distinguished Professor Brian Schmidt, who won the Nobel Prize for discovering our accelerating universe. But first, here's what's current in space.
Time: 7:05 a.m., Friday, December 5th, 2014. Location: Space Launch Complex 37, Cape Canaveral, Air Force Station, Florida. If you were one of the tens of millions of people worldwide who tuned into the launch of the unmanned Orion spacecraft, you witnessed a series of firsts for NASA and for humanity. It was the first test flight of the next generation of human-planned space exploration, the first mission since the Apollo program for deep space, and the first time interplanetary travel has become a reasonable expectation. Mounted atop a Delta IV heavy rocket, the Orion deep space capsule launched over 5,500 kilometers above space, nearly 15 times higher than the International Space Station, spending 15 minutes in the lower Van Allen belt, which is an enormous layer of high-energy charged particles in Earth's magnetosphere. Let's take a brief look at the timeline of Orion's flight. T-7, main engines go. T-0, liftoff. T+3 minutes 50 seconds. Two boosters separate, shortly after Delta IV core stage separates. Fast forward to T+2 hours and 5 minutes. The Orion spacecraft crew module enters the Van Allen belt. And finally, T+4 hours and 23 minutes. Splashdown into the Pacific Ocean after completing 2 full orbits around Earth. The mission was hailed by NASA staff, including Mark Geyer, who is the Orion program manager, as a complete success from a data collection and engineering standpoint. So, how'd they do it? Well, back in 2004, plans were underway to build a CEV, or Crew Exploration Vehicle, as part of NASA's Constellation program, whose ultimate goal was human space travel. Although the Constellation program was actually cancelled due to poor federal funding, the CEV survived to be conjoined with the SLS project. The SLS, or Space Launch System, is comprised of 5 large vehicle configurations designed to lift heavy cargo, including future Orion astronauts, beyond low Earth orbit. When complete, it will be the most powerful rocket on the planet. Aerospace giants Lockheed Martin helped out to give the Apollo command module a much-needed facelift for it to be adopted by Orion. With various other nuanced technologies, like the launch abort system, which actually separates the crew vehicle from the launch vehicle in a case of an emergency, as well as new navigational and guidance systems, the Orion project took shape in about a decade. One critical feature which debuted in the recent test launch was the brand new heat shield. At 5 meters long, it is the largest ever heat shield, built from a futuristic material called AVCoat, or AV coat, which is a honeycomb fiberglass matrix. Now, NASA is learning what it can from this test flight in order to plan a manned Orion space mission with the SLS in 2021. Many mission objectives are still under consideration. However, NASA officials have already stated ambitions of landing on an asteroid or even going to Mars. These are truly exciting times ahead for humanity's future in space. And as Carl Sagan once said, "Sailors on a becalmed sea, we sense the stirring of the breeze."
DNA, or deoxyribonucleic acid, is simply an amazing molecule. It's amazing in that it's the fundamental base of all living things on Earth, containing the biological instructions that make each species unique. For instance, when a cat gives birth to a kitten and not a different animal, that's the work of DNA, having passed on the instructions from adult to offspring during reproduction. Without DNA, there would be no life of any kind, thereby making it a rather durable molecule. And a new study has demonstrated just how durable it truly is, by launching it into space. The study, designated Texas 49, involved an experiment using a rocket and DNA molecules. Specifically, small double-stranded DNA was applied to the outside of the rocket's payload bay and launched into low Earth orbit from the Esrange Space Center in North Sweden. When it descended back down to Earth, the plasmid molecules in the DNA were still found in their application points. Even more astounding was the fact that the DNA still possessed the ability to transfer genetic information to bacterial and connective tissues, providing experimental evidence that DNA's genetic information is capable of surviving the extreme conditions of space and re-entry into Earth's atmosphere. This experiment, dubbed the DNA Atmospheric Re-entry Experiment, or DARE, was actually a spontaneous follow-up to an earlier experiment, conducted by two scientists based out of Switzerland's University of Zurich. This first experiment was also DNA-related, conducted in order to examine the effect gravity has on the functionality of DNA in human cells. But during flight preparations, the pair began to wonder if the outer structure of the rocket could also be suitable for stability tests on biosignatures, which are molecules that can prove the existence of past or present extraterrestrial life. In due course, DARE was conceived and launched, resulting in the astonishing new finding. Due to the fact that almost all of the DNA salvaged from the Texas 49 rocket flight was intact and functionally active, it proves that the life-giving molecule can withstand the most extreme conditions. Indeed, various scientists believe that DNA could potentially reach us from space, as Earth is not insulated against extraterrestrial material that may carry DNA, such as dust and meteorites. On a more concerning note, this extraordinary stability of DNA under space conditions could also signify that it could hitch a ride on the outer hulls of spacecraft from Earth, and thence contaminate the pristine environments of the planets and bodies the craft land on. However, the overall durability of DNA in space is still questionable, as it's unknown if it can survive excessively long journeys through the void. But we know it's possible, due to previous experiments done by scientists who have exposed different organisms to the harsh environment of space, including this latest one. Thus, the case for life in space has grown stronger. If DNA is space-worthy, then it could potentially transport itself to other worlds via impacting bodies, and subsequently seed those worlds with life, thereby promoting the tantalizing idea that life is ubiquitous throughout the universe.
Researchers on the Mars Curiosity rover team have found the best evidence yet that Mars was a wet, possibly habitable world for long periods of time in its history. While there is still no evidence of liquid water or life currently on the planet's surface, a large amount of evidence has built up that Mars had liquid water in its past. That evidence takes the form of various minerals, patterns of sedimentary rock, and old gullies swept out by flowing water. Curiosity has been searching for more evidence on a hill called Mount Sharp in Gale Crater. The rover's team has now found patterns of sedimentary rock which imply that water was flowing into a large lake in Gale Crater for very long times, perhaps tens of millions of years. Sediment flowed into the crater and built up, then was eventually sculpted by flows or erosion into the central peak in the crater, Mount Sharp. Previously, it was thought that Mars may have hosted surface water for fairly short, occasional periods of time. But if Mars actually sustained surface liquids for these longer times, perhaps there were opportunities for life to arise on the planet. Since those days, unfortunately, Mars lost most of its atmosphere, and that tenuous gas and freezing temperatures mean that life can't exist on its surface now. It is still possible that some of that water remains underground, however, and perhaps could even remain as a liquid. In that optimistic case, ancient life might still cling to existence in surprising places. Life on Earth has evolved to survive in the most extreme, inhospitable environments on our planet, so there is reason to hope. When Mars first formed, it would have been fairly warm, largely due to internal leftover heat, but since it is smaller than Earth, it cooled down faster. As its core cooled, it lost the internal dynamo that powered its magnetic field, and when that protective field diminished, much of its atmosphere was swept out into space by the solar wind, or simply escaped thanks to Mars's low surface gravity. Mars now receives too little sunlight to make its surface habitable, and its atmosphere is too thin as well. Nonetheless, the prospect of life in its history and in its future remains exciting. If Mars was alive in its past, that life may have been blasted to Earth by meteorites, possibly seeding Earth and giving rise to the current life on our planet. If Mars can be warmed, and if its atmosphere can be thickened, perhaps by melting its poles, then perhaps it can be terraformed and made livable once again. Mars may be a mostly dead world now, but perhaps mostly dead is not all dead, and hopefully it will have a living future.
Where there's water, there often is life. Scientists have already discovered possible evidence of water on Mars and are seeking to learn if there is life on Mars, or if there had been at one point. To achieve that, they will have to analyze the red planet's past. On our planet Earth, we do this through digs, as generally, the older the material is, the deeper it is. This is no different from what we would like to do on Mars. However, this is not an easy task, as these digs require heavy and elaborate equipment which is difficult to transport to Mars. In order to make digging a bit easier, scientists have developed a cliffbot. This robot will serve in place of robotic or human missions to dig on Mars. The planned use for this robot is for astronauts to lower them instead of being suspended over a cliff themselves. The cliffbot will then use cameras and other scientific devices to analyze locations that are difficult or unsafe for astronauts or rovers to reach. Mars is home to many steep cliffs, some which may have been created through water cutting through the rocky surface of the planet. The cliffbots will be able to explore and analyze these cliffs to find more evidence supporting the possibility of life on Mars. The cliffbot has undergone a lot of testing, and the latest tests were conducted near Efud in the Moroccan desert, where the geology and topography is similar to that of Mars. To simulate an experience as close to the one as astronauts would have on Mars, researchers wore the Auda X spacesuit while operating the cliffbot. The Auda X suit is different from a real spacesuit in the sense that it is not airtight. However, it does simulate the limited dexterity and movement that an astronaut would have in a regular spacesuit that weighs around 45 kilograms. In the new test, the cliffbot was descended to depths of 46 meters, which is 28 meters more than ever before. The robot's also equipped with a HazCam that helps operators see the robot's environment and anticipate any potential hazards. However, as with any new technology, the cliffbot did encounter some problems during testing. At one point, the cliffbot became stuck because a boulder had become wedged between the right wheel spokes, and operators failed to notice it. Proposed solutions include using solid wheels with no spokes and having cameras directed at the wheels of the robot. So what does the future hold for cliffbot? Well, eventually we may see the cliffbot equipped with scientific instruments that are used on other Mars rovers, like Curiosity. More experiments are expected to be conducted with the cliffbot in Utah in 2015.
And that's what's current in space. Dr. Brian Schmidt is Distinguished Professor at the Australian National University Mount Stromlo Observatory and holder of an Australian Research Council Federation Fellowship. In 2011, Schmidt received the Nobel Prize in Physics for his co-discovery that the universe isn't merely expanding, it's actually accelerating in its expansion. Schmidt is Fellow of the Royal Society, a recipient of the Posse Medal, the Dirac Medal, and the Shaw Prize in Astronomy. I'm so honored to be joined here at the Star Spot by Professor Brian Schmidt.
Hi, how are you doing?
I'm well, thanks. Let's start here. A lot of your career has been focused on a mysterious object called a Type 1a supernova. What are those?
Well, we know that they're exploding stars. We know that they are what a white dwarf does when it explodes. We're a little unclear exactly the circumstances by which the white dwarf explodes. But the basic idea is as follows. Our sun, when it runs out of nuclear fuel, the core, the central two-thirds of it, will collapse down to a tiny little object where the electrons push against gravity and essentially make a ball, an ember that cools on forever. But if our sun were created in a binary system, then you can get a situation where that white dwarf, when one of the stars runs out of nuclear fuel, is created, it can end up attracting material one way or another from the other star and growing in mass. And Chandrasekhar showed, and for something that he partially received the Nobel Prize for, that there is a critical point when a star, a white dwarf star, supported by electrons, reaches 1.38 times the mass of the sun, is that the electrons can no longer push against gravity, and the thing would start to collapse. Now, these stars are made out of carbon and oxygen, which still has nuclear energy in it. Just normally you have to make it really hot and dense to burn it. And so as it starts to try to collapse to a black hole, it doesn't reach a black hole. Instead, the whole thing is ignited, and it turns out within a second is consumed by a thermonuclear burning front, also known as essentially a nuclear bomb. So the whole thing ends up being a giant nuclear bomb.
And as fascinating as that is, why is that particular phenomena so useful to our cosmological studies?
So you can imagine you've got this star, which ends up being a giant thermonuclear bomb. So instead of being a bomb the size of what we use here on Earth, you have one the size of the sun or even larger than the sun. So these things are really, really bright. And it also turns out that this process is very homogeneous. That is, no matter how you blow these things up, you end up with this big bomb going out that's more or less spherical because it starts out very small.
So wherever we see these in the universe,
we
can know that they have some constant properties to them.
That's right. And it turns out there's this property which is the more iron and nickel that they create in the nuclear explosion, the brighter they are. So they provide us this cosmic light bulb that instead of being 100 watts is 10 to the 43 watts. And so they're really bright. They're very well behaved. And in the end, it means we can use them to measure distances to about 6% by essentially reading off their wattage from how fast they rise and fall, which is indicator of how big the bomb is.
So tell me now how you use these mysterious phenomena, these supernovae 1A, in the groundbreaking work that eventually won you the Nobel Prize.
So in 1994, when it was realized that you could read the wattage off these things, we knew all we had to do was to look at them and we could measure their distance. Now, since the 1920s, we had realized that the universe is expanding. And indeed, for my PhD thesis, I tried to measure how fast the universe is expanding now. But one of the big questions is, what does the universe do over time? Because we know it's going to change speed over time due to gravity. So imagine that we could measure essentially distances, and it turns out the universe is expanding and that stretches light. So you measure distance, which is equivalent to time, and how fast the universe is stretching, and that sort of allows you to see the trajectory of the universe over time. It's sort of like throwing a ball up and seeing if the Earth is slowing it down, which of course it always does, or in the case of the universe, you don't know what it's going to do, and so the universe might be slowing down a lot because there's a lot of gravity, or it might be slowing down a little bit because there's a little bit of gravity. So we can essentially look back in time with these objects and see what the universe was doing back in time and compare it to the present. So essentially we were able to measure how fast the universe was expanding back in time and compare it to the present.
And we'll get into the startling outcome of that research, but what really intrigued me when I first came upon your research project back in the late 90s was that actually there were two teams that were competing with each other. And I'm really curious, just as somebody who's very fascinated by how science works as in terms of the methodologies of science, how would you characterize that particular relationship between the two teams? Was it sort of a healthy kind of competition, not so much?
So I think in the end it was healthy. I think the competition at the time wasn't always healthy. I think it sometimes was maybe overly competitive, although I was off in Australia and missed a lot of the interactions in North America that took place. But in the end it was set up because in 1994 there were groups coming out of particle physics that had one way of doing the experiment. The group I was part of was astronomers. We had another way of thinking about the experiment. In the end, we had scientific disagreements about what to do. And I and my group was not prepared to cede our vision, our scientific vision, to the other team, and vice versa. So we set up doing independent experiments. And though that competition ended up being good because, of course, we knew if we made a mistake, the other team would correct us in public, and vice versa. But we also sort of learned, sometimes the other team did things we thought were smart, so we of course did that, and they learned from us as well. So it was very healthy. It ended up, we did the work better, faster, and cheaper. And it seems like, well, two people wouldn't be cheaper than one, but the amount of progress and stuff we did, I actually think it ended up being cheaper doing it this way.
Now, given that, as you characterized it, it was more or less a healthy dynamic, and you did have different perspectives that sort of motivated your research, would you say that we should encourage more of this kind of competition in science? Is this generally a good thing in, let's say, physics and astronomy?
So I think in many cases it makes a lot of sense. For example, when you go out and try to figure out if there's a Higgs boson, we didn't just have one team. We had two very separate experiments, and they ended up agreeing. But, if they didn't agree, well, that would have been very important. And in that same way, that dynamic, I think, was very important. This type of competition is important. You don't manufacture it, right? But you don't quash it when it occurs. So I think when there's naturally different scientific perspectives, we need to be able to invest in the different perspectives and not just say, we're going to choose Team A over Team B because we think there should only be one team, even though both of them look very good to us. Sometimes you do have to, in terms of telescope time, share resources. Sometimes you do have to share resources. But not always. And so I think it's a fine line. You really need to look at it on the individual cases.
Now, when you set about doing the experiment, thought that you'd be measuring the deceleration of the universe. And how shocked were you when you realized that the data didn't support that? In fact, perhaps something very different was happening.
So I have to admit, when I first started seeing the data, I was in denial, disbelief. I had assumed we had to have made a mistake.
Right.
And as it became clearer and clearer that we hadn't made a mistake, I was more worried about not what we had done wrong. I was worried about the perception of people who would say, I don't care, you guys have done something wrong. And I was worried literally as being wrong for reasons we couldn't know, that there would be some unknown thing that no one had thought of that would eventually say, well, it's wrong, but okay, you didn't know about it. I was less worried about it being something obvious after spending lots and lots of time.
Trying to find whether there were errors.
We had nailed, in my opinion, every known unknown. Right. But in the language of Donald Rumsfeld, the unknown unknowns always can get you. And I was worried about the unknown unknowns.
When you did finally publish your findings and the other team did likewise, was the scientific community quick to embrace the results because there had been two more or less independent teams that had arrived at a very similar or essentially identical conclusion?
So yes, the fact that there were two teams that had never publicly agreed on things in the past, really on anything, and suddenly agree. Yeah, the two perspectives suddenly agreeing on this, that I think gave people the view that, okay, the basic experiment is probably solid. But we were both using these Type 1a supernovae, so maybe there's something flawed with them. But I think one of the big pushes came from the theoretical community. And there was a problem. There was a crisis in cosmology back in 1995. Things just weren't working right. And this turns out to have solved all those outstanding problems in one swoop. So the theorists of the days who were trying to say, well, our theory just doesn't match up with the data, well, that was because we were assuming the universe was only made out of, dark matter and atoms. So as we added this cosmological constant, the age of the universe started to make sense. Right. Their theory of inflation suddenly made sense. The theory of cold dark matter and the structure of the universe all made sense. So it fixed all the outstanding problems of cosmology. And so the theorists were pretty much, as near as I could tell, immediately said, okay, we're done. This all makes sense. Much more so than the experimentalists like myself, who would have like, well, okay, this is a big claim. We need to check it.
So it kind of fit into this overall picture that was emerging from both the theoretical and from the observational sides.
Yeah, there was this theoretical picture that just wasn't working, and this fixed it. It just sort of said, oh, okay, now it all works now.
Well, since that was, I think, 98, since that discovery, have there been other research projects that have used other approaches other than the supernovae 1A to attempt to falsify and ultimately to corroborate your findings?
Yes, so a number of things have come out. I mean, we've gone through and measured very accurately the matter content of the universe in terms of gravitationally attractive matter, and that's through large-scale structure measurements. And in the end, as you make the large-scale structure measurements, that's how galaxies are distributed across the universe. Those have become sufficiently precise measurements that they can see the presence of dark energy directly in them. The cosmic microwave background, the leftover from the Big Bang, where we look back 13.8 billion years, we see this dim glow of radiation in all directions, makes us believe in the Big Bang. Turns out there are sound waves rippling around in that, and at this point, those observations also provide a very strong corroboration that there's dark energy in the universe. And finally, more recently, there's something known as baryon acoustic oscillations, which are the sound waves left over in the Big Bang. But we can see them in galaxies today. And those sound waves have a scale. And so we essentially have a ruler on the sky that we can go through and measure the size of a ruler from a long, long time ago, closer and closer as we look at closer and closer galaxies. And that, it turns out, allows us to measure the acceleration of the universe in a way that is different but directly similar to the supernovae. And every way we look at it, we get the same answers the supernovae did in 1998.
So the discoveries that you were a leader of your team in 1998, then we have all these corroborations that are happening. So I understand it usually takes a while from the discovery to the Nobel Prize being awarded for it. In your case, it took, about 13 years or so? Yep. Is that typical? Is that because you want to make sure that the discovery is on really solid footing before you award somebody for that?
Well, you'd have to ask the Swedish Academy of their reasoning. 13 years is pretty quick for them. Yeah, and I was a bit surprised, quite frankly. I was very surprised. I agree. I think the experiment had been corroborated. We still don't know what dark energy is, right. And my own view is it's quite likely that in my lifetime we will not know what dark energy is any better than we do now. But predictions like that are often wrong. Fortunately. So, the 13 years, I think, I ended up receiving the Nobel Prize when I was 44, which is very young, So Adam Rees, the other Nobel Prize winner, was 41, and there's only one other Nobel Prize winner around alive who's younger than me, and it's a very young age, so it's a pretty quick turnaround. And, most Nobel Prizes are done by people when they're pretty young. So they often take 30 years to really sink in that they're the right answer.
Yeah. It's an incredible accomplishment, and what I want to ask you about in just our final few minutes is the long-term, the picture that's emerging of the very long-term future of the universe, because we were just talking about the emerging theoretical model, and the accelerating universe supports this idea of dark energy. And what we're understanding is that dark energy is like 70% the mass energy content of the universe. The rest is a combination of ordinary and regular matter. Ultimately, which will win out? Is it now just dark energy that's dominating the universe for the rest of time?
Yeah, so, dark energy is part of space, and so as space expands, dark energy is created with the expansion of space, and no, it does not violate the conservation of energy. It turns out that fact that it makes gravity push is a negative. It's an energy sink, and they counteract each other. So the more dark energy is formed as the expansion of space, the harder it wants to push on space, and those things counteract each other. And the gravitational attraction of you and me and all this other stuff we call dark matter, which we only see the effect of gravitationally, we can't actually lay our hands on as of yet. That stuff becomes less and less important because the density drops as the universe gets bigger and bigger. So right now, it seems the universe is in the process of running away from itself, of getting bigger, faster and faster. That's exponential growth. And we tend to give that the term in the early universe, when we think it happened, of inflation, just like inflation here in an economy. It's the same basic idea. And for whatever reason, in the early universe, it stopped. This time, we don't really know if it's going to stop or not. There's no reason to think it's going to stop anytime quickly, because it's just started. And if it does, that means within, the next 100 billion years or so, the universe will exponentially grow, and all of the things we see in the universe will disappear. They will literally, the light emitted from galaxies we see today will never be able to reach us in the future, because there'll be so much space created between us and those galaxies.
So we will effectively live in an island galaxy.
Yeah, an island universe. So our little part of the universe is not expanding right now. Your listeners are not expanding as they're listening to me. And that's because the forces of gravity and, electromagnetism are too strong in this part of the universe, and our part of the universe collapsed 13.5 billion years ago. That's how the Milky Way was formed.
Right.
But we will look out, see stars, but we will see no other galaxies. Yeah. But I should say, we don't understand what dark energy is. So a theorist might well think that dark energy might decay or change into something. They can make it do anything they want if we give them that freedom. So this is the most obvious extension of what we see now, but it's not set in stone. And it's not clear, how well we can really know, because you sort of have to have an infinite knowledge of everything in the universe to be able to, with absolute certainty, predict the future.
From the talk that I heard you give a couple of days ago here at the University of Toronto, it sounds like you're more optimistic we'll discover dark matter. We'll figure out what dark matter is potentially long before we have a handle on dark energy. Why do you think the dark matter is, an easier project as compared to the dark energy?
Well, I think, we have lots of reasons to believe that dark matter is a particle. And it's a particle that interacts. So up at Sudbury, at the big snow labs, the big underground center that Canada is leading, there's a bunch of experiments to look for these dark matter particles. When they occasionally, we think, interact with normal matter, they'll do a ping, and you can say, I saw a ping. We haven't been able to do that successfully yet, but we have reasons to believe why we might be successful in the future. So that's an experiment we're doing right now that any day could discover dark matter. Dark energy, we have no experiment. The only experiment we know is the universe, because it's so thinly spread. There's a milligram equivalent of dark energy inside the entire Earth. A milligram. That's nothing, right? And it's only when you get to the big expansions of space that it adds up to being a lot of material. And so no one's really come up with a brilliant idea of how to test anything to do with it. So in the end, we sort of know that we have reason to believe that dark energy is something related to quantum mechanics and related to gravity. But we don't have a theory that combines gravity and quantum mechanics. That's sort of the ultimate goal, the holy grail of modern physics. And I have no reason to believe that we're on the cusp of understanding that right now. Now, all you need is one brilliant person to come along, and voila, you suddenly have a breakthrough.
As you said, science sometimes proves us wrong.
Yeah, but we have to realize that we had a great theory of gravity in 1680 something by Newton, and it took till 1915 for Einstein to come along. It could be tomorrow, it could be hundreds of years, or who knows? You just don't know.
I really appreciate you joining us here at the Star Spot, Professor Brian Schmidt.
Great, thank you very much.
Thank you for joining us at the Star Spot, Mind and Universe Continually Expanding.
The Star Spot with Justin Trottier is an astronomy and space-themed podcast based out of Toronto, Canada. Please send comments or questions to starspotpodcast@gmail.com. The Star Spot is produced by Ying Zhang Li. Marketing and promotions by Natalie Morkos. Guest hosting by Denise Fong. News production by Benjamin Jenkins. News contributions from Julia Mazurchuk, Mallory Warren, Jessica Campbell, and Victoria Duncan. Web design by Blair Renault. graphics by Carmina Svillins, and I'm your host, Justin Trottier. Thank you for listening.